the past year, we've been working mainly for DARPA, but Google's also supporting us on hardware acceleration of cortical algorithms, and this is the team members down here. I talked about early work that we've done in this area last year. What we've been doing is taking a set of algorithms that are enjoying success and applying and building accelerators for them. So far, we've worked on Numenta HTM, which you'll hear about this afternoon, and SPARSI, which you'll hear about this afternoon, and building accelerators for those. We've also taken on tasks with a cogent confabulation, which is a Bayesian algorithm, and long short-term memory, which we're starting to look at now as well. And what we've been doing for each of these is we're tasked by Dan Hammerstrom at DARPA to work out the potential for the improvement in the power per unit of performance. So we've actually designed and in one of these built something to demonstrate that. And we've built both programmable versions of accelerators and also non-programmable versions. A basic architecture is relatively straightforward. We have an array of processing elements, which in one case are programmable, in another case are just somewhat configurable. We rely very heavily on processor and memory, which is basically logic that's connected directly to the memory that read and writes to and from the memory directly in doing its operation, thus never uses intermediate storage. And this actually has turned out to be very powerful. At the moment, this is connected to an array of SRAMs. Those in turn are connected to a network, which then go to a global memory over a larger network. So first, the programmable version. This relies on a SIMD compute tile that was designed in a previous project, but modified here. SIMD means single instruction, multiple data. So you operate on data in parallel processing lanes, as they're called. Key to getting the power efficiency improved include shallow pipelines and the use of scratchpad SRAMs rather than caches for intermediate data storage. And this was simulated in 65 nanometers at 32 gigaflops per watt. In contrast, a modern GPU is about 1 to 2 gigaflops per watt. However, very key to improving the performance efficiency of these algorithms was the processor and memory. What we did is we profiled these algorithms on suitable benchmarks in a GPU. From that, worked out the hotspots, worked out additional hotspots based on our own evaluation of major steps in these algorithms, and then made specialized instructions that operate directly on memory in order to speed these algorithms up. For example, B sums across a vector. So, and altogether, these give about a 250x speed up over a GPU. In fact, without these, we only get about a 1x speed up over the GPU and the SIMD processor. This is key to the speed up, though both of these implementations have much dramatically lower power reduction. 3D implementation is key to what we've been doing. In November, we taped out a 2-chip stack that had 2 projects on it. One was a regular heterogeneous processor. The other one was this SIMD engine stacked with SRAM. And that is going to be integrated with the Tezeron DRAM 4, which is a very high bandwidth DRAM, about 4 to 8 times the bandwidth of DDR. And key to actually building these is a very high density face-to-face 3D interconnect technology at an 8 micron pitch called direct DBI, for direct bonding interface. This was done on 130 nanometer because we had to use multi-project wafers, and that was the most advanced node that would let us get whole wafer access to. And the wafers are actually coming back very soon. But as I said, we also implemented ASIC versions. These are designed just to map the algorithms directly onto hardware, pretty much as is. There's some flexibility, but only limited flexibility as compared with a program solution. So we did one of these for SPARSI, which again you hear about this afternoon, and this was implemented with a mesh network of processing elements that map onto the columns within SPARSI. We also did one of these for Numenta hierarchical temporal memory, which is basically a logic design. We found in this case a ring network was more suitable than a mesh network for the local connectivity. The global connectivity is a different network again. We've also been exploring these other algorithms, cogent confabulation and LSTM. With cogent, we actually had the bandwidth to look at a robotic application, which is object avoidance, that is learning the space around you as you move around the space around you. What we do is we have a LiDAR that does a 360-degree scan that forms sentences of information which are used to update the network within cogent, which is a Bayesian algorithm. And using this, we can identify suitable routes through cluttered spaces for navigation of the robot. This brings together what actually are our conclusions for potential for improvement over a GPU baseline. This was run on the KTH video action recognition benchmark. These implementations are at 65 nanometer. We implemented a full GPU baseline. This is in a server class GPU. This was in a desktop class GPU. The SIMD with processor and memory gets a 10,000 improvement in speed per unit of power. The ASIC, surprisingly, is a lower improvement, but that's because it didn't use the PIM enhancements. When those are added back into the ASIC, it will be probably several orders of magnitude better than the SIMD unit. HTM is a little harder to get as big improvement. SPASI has more locality to it, but we're still able to get many orders of magnitude improvement over the baseline in Nomenta as well. And key to all these are, of course, heavy use of the processor and memory. As you've heard many times in this forum, tight integration with memory is important in these applications. Finally, I have two other slides on two different other aspects that we seek collaboration and feedback on. One is with other universities, we're starting a center for application of machine learning, including neuromorphic algorithms, to solve problems in electronic design. There's one such problem presented yesterday that we're not working on that. But problems we're working on include better macro modeling of I/O, IP translation between nodes, and reliability issues. And what we're doing is applying machine learning techniques, including neuromorphic ones, to actually solve problems in EDA. And this center is starting in August 2016 with multiple sources of support. Finally, along with Matt, who's in the back of the room there from Sandia, I'm on the ITRS Emerging Research Architectures Committee, and we just finished a chapter on emerging research architectures. This is the key figure, which includes things done by a lot of people in this room. And if you're interested in giving us feedback on what we wrote for this chapter, we'd be happy to distribute a preliminary version and get feedback on it. What you can see here, of course, is the interests here in this room are towards the right of this chart for the computation paradigms where you either train offline in the case of conventional machine learning or train inline, which of course has been discussed several times today. So thank you very much for your attention. At that point, I can hand it over. Thank you.